organizing this conference. Thanks in particular to Professor Abbassi for the very warm hospitality, and to all of you for the wonderful week here. Okay, better, thank you. So let me start with a very short advertisement about some international cooperation projects that we have, and we'll also present this international center in Trieste, which is called ICTP. Maybe most of you already know its activities. So I'm part of this new working group of the Italian Mathematical Society, which was created just a few months ago, which focus on international scientific cooperation with countries from the Global South. So we just created this group, and we are trying to collect ideas and on how to achieve the goals that we have in mind. These are the main aims that we would like to address. So we would like to be like a reference point for mapping existing initiatives, to collect, I don't know, scholarships for PhD or for master, to have like a sort of list of all the possibilities and opportunities that students can have. We would also like to raise funding, to find new fundings for finance new activities, and we would like to understand which activities and how to develop them. So if you are interested if you want to keep updated, or if you are interested in the activities of the group, this is the website. If you have comments, suggestions, ideas, resources to share, just let me know, or let Diletta Martinelli know. She's the founder of the group, and she's also the responsible. We are happy if we can have a discussion on this. We also created a page with the resources for Palestinian scholars. Again, if you have contacts or resources to share, please let me know, and we will update the site. And the other advertisement is about the activities of ICTP. ICTP is a research center that was founded in the 60s by a Nobel laureate in physics, but it has also some research sections besides physics, in particular in mathematics. It is funded by the Italian government and by the Agency of United Nations dedicated to education, science and culture, and by the International Agency of Atomic Energy. Well, ICTP has several programs that for students and scholars at every stage of the career. Let me just focus on the programs in mathematics. So the one that could be mostly of interest and the postgraduate diploma program. It's a one-year course to prepare the students for the PhD studies with full support, living costs and whatever. After the diploma, there is the opportunity to enroll the PhD degree so the subject is geometry and mathematical physics, and the PhD degree is a joint work with CISA. And after the PhD degree, there are several postdoctoral opportunities. Usually there are fellowships for 2 years with extension. Another program for senior researchers is this program for associate. It works like this. People, so established researchers can apply, and if they are funded, when they are funded, they have the opportunity to visit ICTP every year for like 6 years, and this is a good way to maintain the contacts with the country, and also to have an interaction with another research group. ICTP has, so as I understand, has a very strong connection with many countries in this area, but not with Morocco, and this is the reason for which they would like to empower the connections with your country also. There are other activities from ICT funded by ICTP with some other partners. For example, this researching pair opportunity, and also some of you are involved in the INdAM International Mathematics Master Program, which will take place also in Algeria this year. Last, there are many conferences organized. Well, students are welcome to apply, of course. For example, last year there were 5 conferences in Trieste and several abroad. The contact person, if you want more information, is Claudia Rezzo, who is the head of the mathematics section. Okay, so let's move to mathematics. So my talk will be a survey of some results, some problems and some results that we can ask to study the geometry of Hermitian manifolds. While the results that we will meet are obtained in joint work with several friends and colleagues. Some of them are listed here. So let's start from the beginning to set the setting, to set the context where we work, to explain the problems that we would like to address, and then I will focus on some of these problems. So the context is the context of complex manifolds, especially non-Kähler. So you're probably already familiar with the notion of complex manifold. It's just a topological manifold which is locally modeled over the complex vector space. Locally modeled means, in this case, means every point has a neighborhood which is homeomorphic to an open subset of Cn, and so these are called the local charts, and the transition functions between one local chart to another is given by holomorphic transition functions. So this means that you can give a well-defined notion of holomorphic maps between complex manifolds. Well, you know that the geometry of holomorphic functions is much more rigid than the geometry of differentiable functions. And this also means that it's difficult to construct complex manifolds, and the easiest way is the following. So first of all, the complex projective space is a complex manifold, and this is easy to be proven because if you write down the usual canonical charts, the changes, the transition functions are just rational functions, so they are holomorphic. And also you can take any polynomial, homogeneous polynomial, well, generic enough in order that it has not double roots. If you take the zero set of this polynomial, then it gives a complex manifold. So a natural way, summarizing, to define complex manifolds is to take the complex projective space and to take, well, one polynomial or a set of polynomials generic enough in order that the zero set is not singular, and then the zero set is a complex manifold itself. These examples, which are called projective manifolds, are quite special because they are locally modeled on Cn, not just as for the holomorphic structure, but also in first approximation, also as regards the Riemannian structure, the Euclidean structure. So I mean that these manifolds have a Hermitian metric that locally approximate the Euclidean flat metric at the first order. So these are called Kähler manifolds, and they are quite special because they are at the intersection of several geometric theories. They both have a complex structure and a symplectic structure and a Riemannian structure, and the three structures well interact together in order to give many tools for studying the geometry. So what I'm interested in is trying to study complex manifolds which are not of this kind. And the reason is easy. The reason is that this could give more intuition on what exactly the complex structure implies. So I would like to study the complex structure itself by looking at manifolds which are possibly not of this special kind. So which problem? So again, so the setting is the following in this talk. X will denote a compact complex manifold, with then possibly so whatever, not necessarily of this special type as before. We will fix Hermitian metric on it. Hermitian metric is just a Riemannian metric which is compatible with the complex structure that you have at any point. And we don't assume anything on this metric, so it's not of the special kind as before, it's any generic Hermitian metric that you can define. So what are the possible questions that you can ask? So let's start from the Riemannian geometry point of view. In Riemannian geometry, one usually would like to study, so since there are many metrics, there are many Riemannian metrics, one would like to study some canonical metric. Canonical, well, means that in some sense it is essentially unique, and so it encodes some information on the topology or the smooth structure of the manifold itself. So which condition assures this canonical property? Something that you can ask is to have constant curvature, and there are several notions of constant curvatures that you can define. For example, the first one, the easiest one, is take the sectional curvature, look at the manifolds which have metrics which have constant sectional curvature. Well, you know, this problem is it's very motivated by physics, because if you assume the universe to be locally homogeneous and isotropic, this forces the metric to be of constant sectional curvature. You know, this problem has a very strong answer. So the only simply connected manifolds with the constant sectional curvature are the flat plate, the flat space, the sphere with the round metric, and the hyperbolic geometry. So in this case, the answer is too strong and too. A weaker notion of constant curvature that you can ask is to ask that the Ricci curvature, so the first trace of the Riemannian curvature operator, is constant, which leads to the notion of Einstein metrics. Also in this case, so constructing Einstein metrics is not easy. There are several ways to do this, for example, by imposing some symmetries, and so you can study homogeneous Einstein manifolds, or some symmetry, less symmetry, so a large symmetry group which is not transitive, and so you can study homogeneity 1 examples. Another very interesting tool is to impose, to couple the Einstein condition with another condition, which is exactly the Kähler condition that we said before, and this leads to the notion of Kähler-Einstein manifolds, and Kähler-Einstein manifolds are much easier to be constructed thanks to works by Aubin and Yau. Last problem in order of, so if you want to decrease again the difficulty, so not the difficulty but the level, so you can ask the constancy of the scalar curvature. And this is much weaker problem. You know that, well, it's a theorem by Yamabe, other people after it, that every Riemannian metric on a compact Riemannian manifold admits a conformal change to a metric which has constant scalar curvature. We would like to address this problem also in the emission setting, and we will do this in a moment. So now exactly the aim is to move from the Riemannian setting to the emission setting, and to try to address these problems also in that case. The first issue that appears is that in Riemannian geometry you have a canonical choice for the connection, that is the Levi-Civita connection, the unique connection preserving both the metric and being torsion-free. In emission geometry, in general, you cannot ask, so the Levi-Civita connection does not preserve the complex structure, so it's not compatible with the complex structure in general. And so we are forced to introduce some new connection that will play the role of the Levi-Civita connection in this setting. We want this new connection to preserve the metric and to preserve the complex structure, so to preserve the emission structure in the whole. But of course, this forces the torsion to be non-zero, and so we have this extra issue that appears. And this means two things. This means that there are some technicalities to be solved to deal with the torsion being non-zero, and also that we have non-uniqueness of connection like this. So we'll see in a moment that there is a whole family of connections preserving the emission structures, but with the torsion. So we will focus on the Chern connection, which is one of them, but there are many choices. Let me just recall that the Levi-Civita connection preserves the complex structure only in the Kähler case. Okay, so in the general setting, this doesn't happen. So again, since the Levi-Civita connection is not the right tool in emission geometry, let's focus on connection preserving the emission structure, but possibly having torsion. There are many of them. Usually the way you work with them is not to prescribe the torsion to be zero, you cannot do this, but you can prescribe some component of the torsion to be zero. This element here refers to the decomposition with respect to the complex structure, and this B here refers to the component with respect to the symmetry of the tensor. So connections with this prescribed component of the torsion are called Boudouchon connections, and they form one parameter family. It's important for several reasons. And this one parameter family includes two connections which are particularly interesting, which are the Chern connection and the Bismuth connection. And we will focus on this, on the Chern connection, which is characterized by this extra compatibility property with the complex structure. So the 0,1 component is exactly the Cauchy-Riemann operator of the holomorphic tangent bundle. There are other choices that are interesting in this family. For example, this Bismuth connection is related to physics because, as it was already explained before, the torsion being skew symmetric has important application in physics. So we'll focus on the Chern connection, and many of the results that we will see also apply for other connections in this family. So why we focus on the Chern connection? Because it has a nice formula and nice properties. For example, if you compute the Ricci curvature, so you trace out, we will come back to this point later, but if you trace out a Ricci curvature from the Riemannian curvature tensor of the Chern connection, you find a formula which is very similar to the formula you have in the Kähler case, in the Kähler case. So this in particular is a closed form which characterizes some holomorphic invariant of the manifold itself, which is called the Bochern first Bochern class. Also, the scalar curvature has a very nice formula, which again is reminiscent of the analog formula in the Kähler case. Also, this Chern connection characterize when it is zero, it characterize when it has zero Ricci curvature, it characterize a sort of Calabi-Yau analog in the non-Kähler setting. So it appears also in this, so it has physical motivation, because it can describe these non-Kähler Calabi-Yau manifolds. Well, so these formulas explain why it is easier to work with it. So the first problem we would like to address is the Chern-Yamabe problem. That it's an analog of the Yamabe problem that we said before. So we want to try to understand when a complex manifold admit a Hermitian metric with constant scalar curvature. Okay, so the problem is the following. Let's start from the Riemannian case. In the Riemannian case, it is known, as I said before, that every compact Riemannian manifold admits a conformal change to a manifold with constant scalar curvature. And we would like to address the same in the Hermitian setting. And the first observation is that if you have a Hermitian metric and you apply a conformal change, then you still get another Hermitian metric. So the conformal changes are well behaved with the Hermitian property. So let's fix a compact complex manifold and Hermitian metric on it. We want to study the moduli space of the conformal changes of omega, which have constant scalar curvature. On this space there is a natural action. For example, if you apply an homotety, or if you apply biolomorphic transformation preserving the conformal structure, then of course you still get another metric with the constant scalar curvature. So we are quotienting this space by the natural action of this group. We want to understand whether once fixed a conformal structure of omega, you can construct conformal changes having constant scalar curvatures. And we would like to understand whether this space is non-empty. So if it is non-empty, means that you have a constant scalar curvature metric, whether it is compact or whatever property this space has. So first of all, let me remark that this problem is new with respect to the Riemannian analog, because in general the Chern-scalar curvature, the scalar curvature computed with respect to this Chern connection is write it down easily. So if you compute how the Chern scalar curvature behaves with respect to conformal changes, you find out that it changes in this way, where there is an exponential factor, it doesn't mind, there is the scalar curvature of the original metric, and there is this extra factor, which is a sort of Laplacian. This is called the Laplacian of the Chern connection, and it's given by this formula here. So you see it's given by the standard Laplacian plus a first order term, which depends on this theta. Theta is a one form which is related to the metric omega itself. And this theta plays a role in the following, because there are two special cases that are of interest. First, the case when theta is 0. When theta is 0, well, this is equivalent to show that the form omega is co-closed. In this case, you see the last term disappear, and so the Chern Laplacian is just the Levi-Civita-Laplacian of functions. And the other interesting case is when theta, well, is not zero, possibly, but it's co-closed. And the star of theta is zero. This is equivalent to show that the metric omega satisfies this PDE. And this case is interesting because it makes, when you integrate here, this condition that theta is co-closed makes this term disappear, and then it means that you have a sort of green equality also for the Chern-Laplacian. Metrics of the second kind always exist. This is a very important result by Paul Duchamp. He proved that on every compact complex manifold in any conformal class you can always move to get a manifold with this second property, that the green identity holds. So for this reason, in the following, we are fixing a conformal class. We can choose a reference metric for this conformal class, and the reference metric that we will choose is the only Duchamp metric with volume 1. Okay, so we will exploit, we will take advantage of Duchamp theorem to fix our reference metric in the conformal class. We also are allowed to define a normalization on the solution. It's the following. This normalization is quite artificial, but it will appear in a moment clear why we choose it. So, by exploiting the formula for the change of the conformal change of the scalar curvature, and these choices here for the reference metric and for the normalization, we find out that the solution of so constructing Chern-scalar curvature constant metric is equivalent to solve this nonlinear PDE. And this nonlinear PDE has just to recap, as the Laplacian here, as this first order term depending on theta here, as the original scalar curvature of the reference metric, and there is this exponential terms here which makes the equation to be nonlinear. Lambda here, the constant, the expected constant curvature, has a holomorphic meaning in the following sense, that thanks to the choices we made, this is related to this cohomological invariant of the complex structure, which is an analog of the first Chern class in the Bot-Chern cohomology, and it depends on the conformal class itself. So this lambda is completely determined by the complex structure and the conformal structure. It's not a generic number. So what we are able to do is to solve this equation, at least when lambda is non-positive. So in this case, when the expected constant scalar curvature is non-positive, then by applying the continuity methods and the elliptic techniques, you can show that the solution of this equation exists, and it's also unique up to isometries, of course. So in this case, the Chern-Yamabe modular space is non-empty, so you have a constant Chern-scalar curvature metric, and this constant scalar curvature metric is also unique. The difficulty I will also say something on the case when the expected constant curvature is positive in a moment, but let me remark that this case already includes all the examples where the codirectional dimension is greater or equal than 0, because this expected constant curvature, the invariant here, is related to the volume of any any meromorphic section of the anticanonical bundle. So when the Kodaira dimension of the manifold is greater or equal than 0, then every conformal class has this property here. As for the positive case, the difficulty is that you cannot apply the maximum argument, the maximum principal argument at some point. So we have some examples. We have some techniques to construct new examples from known ones. But the main problem is that, so in the Riemannian case, this case is studied by variational techniques. Here in general, the problem is not variational. Instead you have an extra condition on the metric, which is the balanced condition I stated before. So in general, the problem is not variational, so you cannot apply variational techniques. In general, you don't have uniqueness, so uniqueness for sure is not does not hold, and this is again by, as in the Riemannian case, by applying bifurcation theory. And we have compactness if volumes are bounded. So let's move to another problem, which is the Chern-Einstein problem. So Einstein metrics in the Riemannian case again are very well motivated by physics, because at least in the case when lambda is 0, asking for Ricci curvature equal to 0 has several meanings. First of all, is related to the Einstein equation of gravitational theory. So Einstein metrics in the Lorentzian case are a solution of the Einstein equation in the vacuum with zero energy stress tensor. And also in the Kähler case, in the complex case, they are also related to physics in another sense, because they are related to a restriction of the holonomy, and the restriction of the holonomy is related to some gauge theory for the manifold itself. So we would like to extend the problem of finding the Einstein metrics in the complex setting, but in complex non-Kähler setting. So here the main issues are two. First, that you don't have a unique way to trace out a Ricci curvature from the Riemannian curvature tensor. So you have several, because now you lack the symmetries of the curvature tensor. So you have several ways to trace out a Ricci curvature from the whole Riemannian curvature. Essentially, there are three different ways. The third one, I don't understand the geometric meaning, so we will focus essentially on the first one and the second one. I will write them later. And second problem is that you don't have a Bianchi identity for the Chern curvature. So in general, the Einstein factor, what is called the Einstein factor, is not necessarily constant, so it's a function. So you have many Einstein problems in this setting, because you can choose which Ricci curvature to consider, and you can choose whether the Einstein factor should be constant or not. So let's start from the first Chern-Einstein problem. So now we are tracing the Riemannian curvature in the geometric part, in the form part, in the first two indices. The indices that are related to the form part. In this case, this case is not really interesting, because there is nothing new. I mean, if lambda, so if you are assuming that the Einstein factor is constant, not necessarily constant. If you are assuming that the lambda factor is not 0, then you can see that there is a conformal change to a Kähler metric. So since we are interested in manifolds not admitting any Kähler metrics, we are not really interested in this case, because here you can show that you can always perform a conformal change to get a Kähler metric. And so the only case of interest in this context is the case when the Einstein factor is identically 0. And this case was studied by Valentino Tosatti, and is called the case of non-Kähler Calabi-Yau manifolds, which are in a sense a generalization of the Calabi-Yau manifolds in the non-Kähler setting. And this case is completely understood because the existence of metrics with 0 first Chern-Einstein Chern-Ricci curvature is completely characterized by this holomorphic invariant. So this case is easy. And the second problem is when you instead of taking the trace in the first two indices, you take the trace on the endomorphism part, on the second pair of indices. So in this case, this problem is conformal. It's well related to the Chern-Yamabe problem in the sense that you can always assume lambda constant if the Chern-Yamabe problem has a solution. So when the Chern-Yamabe problem has a solution, there is no difference in taking lambda function or lambda constant. This case is so the problem is a very special kind of Hermitian-Einstein matrix. So there are obstructions coming from the Luke and Bogomolov concerning the existence of Hermitian-Einstein manifold matrix, and there are also obstructions coming from conformal theory. One can construct examples on homogeneous spaces and also on spaces with a large isometry group. In general, we are not able to attack the problem in full generality. So as far as now, we only have some construction and some examples. Okay, let me just introduce another tool that we have to investigate canonical Hermitian matrix, that is the Chern-Ricci flow. So let me start from what happens again in the Riemannian case. So in the Riemannian case, a very powerful tool that was studied in the last decades was the Ricci flow. And the Ricci flow is an evolution equation for metrics, for Riemannian metrics. It evolves, so it's a family of Riemannian metrics solving this parabolic equation, where, so in a sense, we are evolving initial Riemannian metric by moving in the direction given by its Ricci curvature. This problem, well, you know, it's very, this tool is as shown to be very powerful, for example, for solving the Poincare conjecture and so on. The issue in the Hermitian context is that even if you start from an Hermitian metric, the evolving metrics are not longer Hermitian. Unless some extra property on the initial metric is assumed. For example, if the initial metric is scalar, then the evolving metric remains scalar for every time. But this is a very special case, and is called the Kähler-Ricci flow. If the original metric has some other symmetry in the curvature, which are called the Kähler-like conditions, then GT remains Hermitian for every time. But in general, if you start from whatever metric, initial metric at the beginning, the evolving metric is not longer Hermitian. So there were several solutions to this issue that were proposed. For example, Stritz and Tian, they suggested to consider some Hermitian curvature flows. It's a family of different flows that can be defined, and they are useful for different problems that you can want to attack. Today we focus on this other solution, that is the Chern-Ricci flow. The Chern-Ricci flow was proposed by Gill and then studied by Tosatti and Weinkoff. It's just similar as before, but you are replacing here the Ricci tensor with the Chern-Ricci form. So instead of taking the Ricci curvature computed with respect to the Levi-Civita connection, again we are just computing the Ricci curvature with respect to the Chern connection. Well, this flow is expected to be useful because the idea is that the behavior of the Chern-Ricci flow in some sense reflects the underlying holomorphic geometry of the manifold. So we expect that if we start the flow and we look what happens at the infinity, and so at the infinity or when the flows has some singularity, then we can understand some property of the holomorphic manifold itself. In particular, this could be useful to understand and to classify compact complex surfaces. So let me just recall that the classification of compact complex surfaces is still an open problem, because so it was started by Enrique Scodaira, CEO, and many other people. It's essentially well understood, except for this last class, when the Kodaira dimension of the manifold is minus infinity. So in this case, there is a partial classification. It is known that when the second Betti number is 0, then you only have the off surface and the in-over surfaces. But when B2 is positive, the second Betti number is positive, I still don't know whether the cutoff surfaces, which are the only examples that we have until now, I still don't know if they are the only ones. So I still don't know if whether there are further examples besides cutoff surfaces. And so one can try to apply the Chern-Ricci flow to the above examples. For example, let's start from the in-over surface. I don't want to, so maybe I'm already out of time. But, just to say, to give an idea of how it works, these surfaces are a very good geometric description, because on the one side they can be described as differentiable bundles in this way. This is just differentiable, no? There is no, it's not an holomorphic bundle because the base is not even dimensional. But on the other side, they also have a very good structure from the point of view of complex geometry, because they are endowed with an holomorphic foliation. And these two different structures are interconnected because the leaves of the holomorphic foliation are dense in the fibers of the differentiable bundle. So these manifolds are, are exactly here. So in the well-known part of the classification. But we will start in studying this special case in order to understand whether the Chern-Ricci flow can give us some intuition on the geometry also of the remaining ones. So what you can prove here on this in-over surfaces is that if you start from the most natural and most homogeneous manifold metric that you can define, which is called the Trichari metric, whatever it is, then, well, in this case, the flow just becomes an ODE, so an ODE, and so you can solve it explicitly, and you see that the solution of the flow converges to this form alpha, which is related to the holomorphic foliation, because this alpha is the form generating the holomorphic foliation. And from the point of view, so if you look at the Gromov-Hausdorff convergence, then you see that the corresponding metric spaces converges in Gromov-Hausdorff sense to S1, which was the base of the bundle. So you both recognize the holomorphic structure and the differentiable structure by looking at the behavior of the flow. And this happens in general for any locally homogeneous metric. What we can prove, what we proved with Valentino Tosatti, is that the same behavior works for any, when you start from every Kudushan metric. Kudushan metrics were the same as that we already met before. Just to give an idea of the proof, this is related to the existence of what are called metrics, which are flat along the leaves. Well, strongly flat along the leaves, because for this, it's another problem that you can, so if you find a metric which is strongly flat along the leaves, then you have a good behavior for the flow. Finding a metric with this property just reduces to solve a PDE like this, which is a degenerate elliptic equation in U. You can solve the equation just by exploiting the symmetry of the fibers. The fibers were tori, and so by applying Fourier expansion on the fibers, you can just reconstruct the solution. Something similar happens also for other manifolds, other surfaces, but this is just technically more complicated, but it's essentially the same. Well, what we would like to do is to try to understand what happens for surfaces of Kato type. So in the class 7 classification, there are of manifolds of surfaces, Kato surfaces, and then maybe some other examples that can arise in the future. But we would like to address the similar questions for the Kato surfaces. Other problems, just to give more ideas, is to try to relate the existence of these canonical metrics maybe to some cohomological property. So for example, the first problem here exactly relates some cohomological property of the manifold to the existence of some other canonical metric on the metric itself. In all these problems, convergence of the Ricci flow, solving elliptic PDE on manifolds, etc., a technical issue that always appears is that you cannot control the volume of metric like this when you change a file. So this is another interesting problem to understand how to relate volumes or other metric invariant to holomorphic geometry of the manifold. Okay, sorry for the confusing talk. Thank you for the attention.